1/2. So don't forget, multiply by that extra factor of 1/2 there. And now we have dr ds. And again, since we're integrating over a rectangle, the integration order doesn't matter, as long as you respect your bounds and everything. Okay, so let's go ahead and integrate this. If we integrate with respect to r, okay, this technically is a constant, so you're going to get integral from 0 to 2. Actually, I'm going to write this stuff up. Yeah, let's write this up front. S e to the s squared, r to the 6 over, now we usually divide, right, by 6, but then we have that 1/2 there, so I'm just going to write 12. Okay, evaluated at 2 and 0. ds, if you plug 2 into this, you're going to get, I got to think for a second. See, 2 to the 6th power is 4 times 4 times 4, so that's 64 over 12. Okay, let's pull out this constant. So we'll get 64 over 12 times the integral from 0 to 2, s e to the s squared ds. Let's use a little bit of u substitution there. Let's let u be s squared, then du over 2 is equal to s ds. Okay, so this integral will become 64 over 12, integral from 0 to 4. Okay, remember we're changing our bounds here because we're doing a u substitution. E to the u, du. So this will be 64 over 12, e to the 4 minus 1. Boom. Okay. Now what I challenge you to do, if you really want to go for it, try integrating this without doing the substitution, and then just sort of compare how nice it was doing this change of variables. I think you'll find out pretty fast that this is a lot nicer. All right, so let's shift gears. So if we're doing the 3-variable case, okay, so let's suppose that we're computing a triple integral and we want to do a change of variables, then we would still have to multiply. So if we have the triple integral over some volume f dA, and we convert this by our change of coordinates, we'll have to change probably the solid that we're integrating over. F, we are going to have to multiply by something, and that something is given by the 3-variable case Jacobian, okay, which hopefully you see looks very, 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 very nasty. We'll see a better way of thinking about this so you don't have to memorize a formula like that. But in any case, if you're dealing with a triple integral and a change of variables, it's the same thing as in the 2-variable case, except your Jacobian is going to look a little bit nastier. Okay? So again, if you do your change of variables, the triple integral, the resulting triple integral will be, so you substitute your x, your y, and your z's. You also have to figure out what happens to your region as well. Don't forget that. And then don't forget to multiply by the absolute value of this Jacobian here. Okay. But like I said, this Jacobian here is a beast. And there's a better way of thinking about it. So we're going to think about the Jacobian as the determinant of a matrix. So hopefully you remember back in cross product, I did mention this briefly, that the cross product is the determinant of a certain matrix, right? We're going to think about the Jacobian in a similar way. Okay, so if we're dealing with the 2x2 case, okay, we can think about this Jacobian as the determinant of the following matrix. Now, if you're unsure of what a matrix is just a rectangular array of entries or numbers or things. So for instance, 1, 2, 3, 4, this would be a matrix, a 2x2 matrix. So and with the entries 1, 2, 3, and 4. Okay. So the Jacobian can be thought of the determinant of this matrix. Okay, so the first row, we're taking all possible partials of x. So dx ds, dx dt. And in the second row, we're taking every possible partial of y. So dy ds, dy dt. Okay. And then the determinant of a 2x2 matrix is you just multiply the diagonals and subtract. So the determinant, which we use vertical bars for as well, this is dx ds, dy dt, minus dx ds, dx dt. So we're doing this diagonal right here, dx dt times dy ds. Okay, so for 2 by 2 matrices, the determinant's really, really nice. You just multiply the diagonals and subtract. Now, when you increase the dimensions of your matrix, this gets a little bit more complicated. So if you're dealing with a 3 by 3 matrix, A, B, C, D, E, F, G, H, I. Actually, let's not use I. Let's jump to L. So if you're dealing with a 3 by 3 matrix, the determinant, again, is a little bit more complicated. So the determinant, to figure out the 3 by 3 determinant, what you do is you start, and you'll learn in linear algebra, you can actually do this a lot of different ways, but the way we're going to do it here, we start with the first entry here, A, and we're going to get rid of that first column and first row, leaving us with a 2 by 2 matrix. So the first part of the determinant is going to be A times the determinant of the matrix E, F, H, L. Okay, so that's our first term of the determinant. Our second term, we're going to move down the row to B, and we also, by the way, we're going to change signs here. So minus B times, get rid of that second column, first row. What's left over? D, F, G, L. And then finally, move down to C. We do plus C because we're alternating signs. Get rid of that first row, third column. What's left over? D, E, G, H. Okay. And then, using what we know about 2 by 2 determinants, this becomes A times EL minus FH minus B times DL minus FG. That should be a plus there. Plus C times DH minus EG. Okay. So that's a 3 by 3 matrix determinant. Again, it is a little bit more beefier than the 2 by 2 matrix, but imagine doing a 4 by 4. 4 by 4 is defined similarly, except you have 3 by 3 determinants going on everywhere. So in any case, going back to our Jacobian here, okay, here's the 3 by 3 Jacobian. You can view this as the determinant of the matrix. So the first row, we're taking all possible partial derivatives of x. Then the second row is all possible partials with respect to y. Oops. And then the last row is all partials of z, all possible partials of z. dz, dt, dz, du. So the Jacobian, this thing can be thought of as the determinant of this 3 by 3 matrix here. Okay? Which, again, to find that, you use this formula here, which hopefully you see. I want you guys to take a look at this. Okay? And then compare it with this right here. Okay? Notice it is the same thing, except, well, we have partials here instead of just letters.